This course looks on the wireless sensor networks which are today integrated in the Internet of Things. This course module is four-parted. First, a motivation for wireless sensor networks is presented with basic terminology mentioned for better understanding in the application section. Second, the big topic wireless sensor network is introduced, covering basic hardware and software requirements and solutions. Third, different applications are briefly described, what wireless sensor networks are developed for, and what will be the future. A brief overview is given in the right side in the figure, where you can see the main purpose is monitoring and localization. Finally, the course is summarized to point out the main things you should remember after this course. Let's start with motivation. Due to the decades, the Internet grew as well as the availability and the connectivity of devices of different diversity. Those devices can be servers, PCs, notebooks, mobiles, and sensors today. Together with this development, also the variety of application raised, starting by personal networks over worldwide networks, low security applications up to high-risk applications. In the fourth part of this course, different applications will be presenting, covering all those topics. The challenge with wireless sensor networks, just mentioned in short here, will be their constraint in resources for battery, memory, and computational capacity. Also, usually they include sensitive information like IP addresses, your individual ID, phone numbers, and measurements at the same time. So, not everyone wants to read it or should read it. Keep it in mind. First of all, it has to be mentioned that today the community is speaking of the Internet of Things, as illustrated here by the figure. This term was first mentioned in 1999 by Kevin Austin in the RFID journal. Under the term, all devices are included which support IP communication. As you can see in the graph, different groups exist within the Internet of Things: service sectors, application groups, location, and devices. For example, the service sector, marked pink and called IT and networks, can be separated into public and enterprise application groups, which can then be specified by locations such as services, e-commerce, mobile carriers for public applications, and into IT data centers, offices, private nets, mainly for enterprise solutions. All well-known devices like servers, storage, PCs, switches, and so on can be used here. Other service sectors can be found in health, building, industry, or transportation. If you speak about device deployment in systems where collaboration of computational elements controlling physical entities take part, we are speaking of so-called cyber-physical systems. An intuitive example for such a system is a home automation system. Imagine you have sensors in a room measuring the temperature, transmitted to a central unit, which is configured by the inhabitants in the flat or in the house, with room temperature settings for each room. This central unit compares the received value with a set one, and depending on the result, an action is planned and executed. If the room temperature is below 23 degrees, the heating control is activated and windows are closed if the setting says it should be warmer. The measurement is repeated periodically so that a circle of actions take place, which is illustrated in the figure in this slide in the right corner of it. In order to integrate many different devices like handhelds, mobiles, or sensor networks in those systems, the development must be aware of the following requirements: standardization, which means use solutions which are usable on different devices. Resource efficiency is important due to the fact that some devices have limited resources such as memory, energy, or computational capacity. see sensor networks. In order to support a long life without manual interfering, you have to think about the protocols you are using. Under the term usability, it is requested to use a common communication solution like IP communication, perhaps today even require IPv6. The other part is look on flexibility. Flexibility is the basic idea of Internet of Things, which means to support solutions which can be used for different applications with less adjustments for new vendors. So, you are speaking about a cycle in the cyber-physical systems, looking on computation, control and communication at the same time. This figure should give you a brief overview of available cyber-physical systems in order to receive a feeling where you find them, but perhaps not recognizing them. So as you can see, you get in contact in different areas. Robotics, healthcare, also in today's bus system, but all have in common you have to think about sensing, how you can secure it, which application do you have, how should it scale in the network, look on communication you want to support, and also look on hybrid models as well as on control systems. In the following we will focus on the light blue area, where most of the wireless sensor systems are deployed today, and on what we are focusing in the rest minutes of this course module. Let us now go to the second part of this course, presenting background information about the wireless sensor networks as a subgroup in the Internet of Things. On the right side you see common used sensor network with different hardware, which size from matchboxes to coins, and all are battery powered. The goal of this chapter is to give you a brief understanding of wireless sensor networks. The idea of wireless sensor networks is to interact with the environment as briefly mentioned in the home automation example in cyber-physical systems. As you can see in the figure below, in the gray areas, wireless sensor networks are usually embedded in an environment, for example living room, field or greenhouse. Those sensors measure environmental data such as temperature, gas concentration, pressure, brightness or humidity, among others, and transmit their data to a central unit, usually called sink. This central unit is marked here in red, called gateway, which consists of a node wired connected to a server. This entity complex is responsible to make the data available to other entities, like different applications, which will be introduced later. This entity complex processes data into a format which are requested of the application, is stored and deployed. The figure on the last slide indicated that participants in a wireless sensor network have different roles. Let's focus on them. First of all, we have the sources. Those sources are all sensor nodes within the wireless sensor network that measure data or intermediates on the communication way to the sink. They can be equipped with microphones, video equipment, or temperature sensors, for example. Depending on the distance between data measurements, entities and sink intermediates can be without sensors, just with a task to forward the data towards the sink. As a sink device are named, which receives the measured data. This can be, as mentioned, the global sink in the gateway complex on the slide before, but also your PDA or notebook. Usually a sink can be all devices that can receive data via wireless connection. In a cyber-physical system, the last role is occupied by an actor. Depending on the received data, an action is performed, here, for example, giving an alarm or not, as indicated with those two figures on the right bottom. After a basic overview of wireless sensor network structure in the slide before and role of devices, let's look on hardware. The hardware is one of the basic things you have to look on when you want to deploy a network and to manage tasks within the network and for a special application. The hardware of sensor node can be divided into standard and optional equipment like microcontroller, memory unit, communication device, the radio, power supply, and sensors and/or actors. The most important equipment here is a microcontroller, which is responsible for data collection, processing, decision management, and flow control. Optional equipment can be LEDs giving you an optional feedback if everything is working as requested, power switches, external power connectors and RF connectors, for example solar panels, or expansion connectors. This table gives you an example for hardware which is used usually at the university area of research. Here you have sensor nodes going from coin-sized to matchbox sizes. As you can see, we are speaking of limited resources on memory, going from 8 kilobyte up to 512 kilobyte. They are usually powered with batteries or extension cords for the USB to a power plug, and they include different sensors ranging from light, acoustic, up to humidity and GPS. Furthermore, they support different sleeping modes, which means they are low active and do not consume as much energy as full powered. And also those devices are available from different vendors. Different hardware also requires different operating systems. In general, they have a modular structure, but may include constraints for hardware, programming language, and supporting of resources. For example, TinyOS was especially developed for hardware from Crossbow, like Iris or Telos B modes, listed in the slide before. It uses NetC, a programming language similar to C. In contrast, Contiki is Java-based and supports a different range of sensor nodes like Telos B or special developed hardware. Other known operating systems for sensor networks are LightOS and Mantis. The development of a program within the operating system follows the design graph on the right side of the slide, starting with the application, modeling of solution, deployment and data collection, resulting in an analysis of data and data collection in order to optimize the program. When thinking of a wireless sensor network deployment, the environment and requests by the applications are important. Therefore, you have to think about characteristic requirements which must be faced. Those are presented now. Looking on the quality of service, you have to think about traditional quality of service metrics that are not able to be applied here. Still, service of wireless sensor networks must be good. Right answer at the right time. That's essential. Fault tolerance is another aspect. The solution has to be robust against node failure, like running out of energy or physical destruction. Lifetime means the network should fulfill its task as long as possible. Definition depends on the application. Lifetime of individual nodes are relative unimportant because you should support backup solutions, but often treated equivalent to the fulfillment that the network should work as long as possible. Other aspects are scalability. That means you should support a large number of nodes. Furthermore, the wide range of density must be taken into account. So, waste or small number of nodes per unit area are required, and this is very application dependent. Programmability is essential. This means you should update it during runtime, so reprogramming of the nodes in the field might be necessary, so improve flexibility. Furthermore, maintainability is required. This means wireless sensor networks have to be adapted to changes, self-monitoring, or operations if they change. This requires an incorporate possibility for additional resources that can be adapted or deployed by new nodes. In order to meet the aforementioned characteristics, the following requests must be addressed: multi-hop wireless communication, energy-efficient operations, auto-configuration, collaboration, and in-network processing. Operators set a high standard to good support of quality of service, energy efficiency, and scalability of the performed functionalities. In order to accomplish the operator's requests, design principles are important. Those are network organization, in-network processing, accuracy, and data centricity, which are described in the next slides. Before implementing the application, you have to think about essential design principles and how to address them. Let's look on them. Network organization has a goal to quick data transmission support towards the data sink. This can influence the performance of the sensor network itself. Distributed organization combined with self-organization protocols is the key here. Neighbor discovery algorithms and routing protocols both support the establishment of a stable communication network and support efficient transmission. In-network processing has the goal to save resources and to reduce the traffic within the network. Therefore, you have selected nodes in the network performing special algorithms like aggregation or compression of the data. Usually, those nodes have more resources for calculation and buffer purposes as usual sensor data collecting nodes. Data centricity addresses the data instead of the source for transmitting. Furthermore, we have accuracy in the design principles. Here the goal is to ensure long lifetime of all network participants. Therefore, the data transmission must be efficient and resource-saving at the same time. Taking current network status into account is essential here. This means optimizing routes and avoid nodes with less resources and also to avoid overloading special routes. As you can see, design principles are differently weighted according to the chosen application scenario, the performed functionality, the network size, and the resources of the hardware used. So keep those principles in mind when you develop a network and think about the application. Now you have a basic idea of the terms Internet of Things and cyber-physical systems, as well as a basic understanding of requirements of wireless sensor networks and its resources. The things introduced in the last minutes are essential for understanding the application development. In the upcoming part, different existing applications and their characteristics are introduced in order to get a feeling how present the technology is and already used for common sense. For wireless sensor networks, different deployment solutions exist. For example, dropping them from an aircraft, you are speaking of a random deployment. Usually, uniform random distribution for nodes over finite areas is assumed in this case. Is that a likely proposition? Answer yourself. Well, planned fixed deployment is usually used today, so you are speaking of a regular deployment. Example would here preventing maintenance or similar areas to support. Not necessarily geometric structure is required here, but that's often a convenience assumption. Just think about the example at the beginning of this course with the room temperature in your house. The third deployment option looks on mobile deployment. Those mobile sensor nodes can move to compensate for development shortcomings. They can be passively moved around by some external force, for example wind, water. They can actively seek out interesting areas. Examples would be here firefighters that deploy sensor networks, or if you want to monitor the habitat of animals in their life surroundings with less manual interruption. Looking on literature, you can find different strategies to group the applications where wireless sensor networks are involved. The grouping has in common that interaction patterns between sources and sinks classify application types. For example, event detection. Nodes locally detect events, maybe jointly with nearby neighbors, report these events to interested sinks, and continues. Event classification is another option. Usually you have periodic measurements. This means the reporting is done in intervals, which are pre-deployed. Function approximation is another option. Here, use sensor networks to approximate a function of space and or time. An example would be a temperature map. Edge detection. Find edges or other structures in such a function. For example, where is the 0-degree borderline? Finally, we have tracking. Report position of an observed intruder, for example in military, or report where your car is or where your pet is. This slide gives you a first impression of existing applications of wireless sensor networks, starting with monitoring tasks in general areas like structural health monitoring, habitat monitoring, or health applications. Other applications can be found in emergency scenarios, logistic and military areas, as well in automatization issues in home or industrial scenarios. The following slides look a little bit deeper in several applications. Let's look on structural health monitoring. Here, the data sink and the sensor nodes are fixed, so they are deployed on well-known positions which can be located with a map or GPS. So location information is known before deployment. The goal here is the observation of building structures, for example on bridges, skyscrapers. Analyzes changes in the structure of the building which can affect the performance and the architectural stability of the construction is here the goal of the research. Examples can be found, for example, in Asia, looking on skyscrapers, or in the US, looking on bridges, as here shown the example of the Golden Gate Bridge in San Francisco. Let's look a little bit deeper into the Golden Gate Bridge project located in US San Francisco. Here, the idea is to observe the ambient vibration of the bridge. The bridge itself is located in an area where earthquakes and sharp sea winds often occur that might damage the construction itself. The idea of the deployment is to measure two directions of the bridge span, one up-down and one across the span. Therefore, different accelerometers are deployed on different stages on the bridge. Accelerometer type 1 is responsible for recognizing big movements like it happens in earthquakes. The accelerometer type 2 is responsible for narrow ranges, so for ambient vibrations which can occur because of car traffic or wind. In total, as you can see on the right picture, the dimension of the bridge requires lots of sensor nodes that has to be deployed. In total, 50 nodes of type Berkeley modes are deployed. They are building a multi-hop network, and the longest hop distance is 280 feet. For communication, they are using IEEE 802.15.4 at 2.4 GHz. It's a bidirectional communication established in the network. This means not only the sensor nodes are reporting to a sink, which then forwards the data, for example, to a lab, to analyze the data. Furthermore, the persons in the lab can directly communicate to the sensor nodes and there they can update the measurement intervals or, for example, shut them off if they are running out of power. Bidirectional communication is essential when you want to control your network when it is running. For example, if you want to update measurement intervals from 5 seconds to 10 seconds, which makes sense when you are looking on emergency cases. Another example for monitoring is the so-called habitat monitoring. Here you monitor the behavior, for example, of animals. The goal is to monitor without environmental impact, which might occur when you have to change batteries. The deployment is, compared to the structural health monitoring, a little bit changed. Here the sensor nodes are partly mobile. The sensor nodes must resist different environmental impact, for example, wind, rotation, movement. Because of the mobility of the sensor nodes, the sync might not be in the communication range all the time. Therefore, the data has to be buffered for later communication and transmission to the data sync. Relevant projects in this area are the ZebraNet, Great Duck Island project and the UVA bird tracking system. We will focus on those in the next slides. Let's look on the ZebraNet, which was deployed by the University of Princeton in the USA. They want to observe zebras in Kenya. Here, the idea was just to equip the males with a sensor collar, because the males are responsible for the group movement. The tracking collar weighs 1090 grams, which is quite heavy when you compare it to the seabirds in the next example. Those collars are equipped with a GPS chip, a CPU, 640 kilobyte flash memory, include a short-range radio unit as a long-range unit, and are powered with lithium-ion batteries, which are adapted to a solar cell array, which allows the recharging. The idea here is to make a long-time tracking available for those zebras, which might be a long distance, for example over 100 kilometers, until they reach a sink where the data can be transported to. The idea is that the ranger serves as a mobile data sink in this case. This means the ranger drives to well-known places, such as a waterhole, and waits until zebras cross the range of the data sink. The data sink announces itself permanently to the environment. If a collar detects this signal, it transmits all its data automatically. To ensure that all collected data from all collars reach the data sink, even if they are not in range, collars transmit some data to other reachable nodes in their surroundings, so you have a kind of redundancy in this case. Another example for habitat monitoring is the mentioned Great Duck Island project. On Maine's Great Duck Island, biologists put sensor devices in the underground nest of the storm petrels, and on 4-inch stilts placed just around their burrows. The devices record data about the birds and relay it, bucket bridge style, to a gateway node, which transmits the information to a laptop in the research station, then to a satellite dish, and ultimately to a lab in California, where the behavior and the occupancy of the burrows are analyzed and logged. The third example for habitat monitoring is the UVA bird tracking system from the University of Amsterdam, Netherlands. Here the idea is to better understand the migration and the navigation of the birds. In order to observe such small animals, lightweight hardware must be developed. The hardware utilized includes a triaxial accelerometer and a GPS logger. It is powered by solar and rechargeable batteries, which ensure a long lifetime. Bidirectional communication between the base station and the mobile bird hardware was established in order to allow updates of the system. The data sync is represented by mobile ground stations, which further transmit the data to the labs using satellite connections. Received data is automatically processed and visualized in the developed virtual lab, as shown in the figure here. Beyond animal observation, habitat monitoring can be applied to humans as well. An example is elderly assistance systems combined with home automation support. The goal is to support elderly and disabled people to stay in their home as long as possible. Therefore, the home is equipped with intelligence going from sensors to automatic systems that send out an emergency call when something is wrong. Let's give an example. You have an intelligent carpet in your home equipped with sensors that recognize when you fell down and stop moving. Automatically, an ambulance is called to save time and to rescue. Other examples are intruder detections or light activation in the night when entering a floor. The overall goal is to give you a safe feeling in your flat. Sometimes those habitat monitoring issues are combined with the internet to ensure contacts to other friends or people in your surrounding. Wireless sensor networks can also be applied in health applications. In this case, we are speaking about wireless body area networks. The idea here is that human functions are observed by sensors, and the data is directly transmitted to an analysis facility. Here we have two main areas: the private commercial applications and medical applications. Example for private commercial applications are the Nike Plus or the Adidas solution, which recognized where are you walking, watch your heartbeat and map it to your sports activity. For private applications, you can look on the Nintendo Wii station. So when you are playing, you have a sensor in your hand and the Wii recognized what movements you are doing, and finally on the screen you see how your thing in the screen is behaved. An example for medical applications is the control of newborns. So there you really want to measure the heartbeat and directly send out an emergency call when something is wrong. Other examples can be found in emergency alert applications. Here the sensor nodes are located in a fixed position. For example, in the measurement buoys at the sea, or sensors next to known regions for earthquakes, such as volcanoes or seismotectonic active regions. The idea is to measure water, sea ground, or earth movement to predict an emergency case. The data is transmitted to a data sink located in a research center at the land surface where data is analyzed. Depending on the data changes, researchers can predict an emergency case, for example a tsunami or an earthquake. Early warning systems, which are integrated in online applications which are available for devices like the mobiles, are then activated. As a result, an early evacuation of the people can be done. In logistic applications, the data sink is generally fixed in the transport vehicle. Sensor nodes are on the transport materials such as packets or boxes. The sensors are equipped with a GPS unit, with a radio frequency identifier unit, or with vibration sensors, for example. One of the challenges of this setup is the question of self-organization. Boxes might be loaded randomly. Boxes must organize a working infrastructure by themselves in order to ensure a working network to transmit data to a data sink. If a box is moved, its location and communication links need to be updated. Military applications have three purposes. First, monitoring militant activities on roads or in villages. Second, intrusion detection. And third, protection purpose by observation of surroundings. Here, the data sink is located in the headquarters, so it's fixed. Flying objects, like aerial drones, are equipped with different sensors, such as GPS and infrared sensors, in order to observe the region. They are usually unpiloted and fly over the region of interest in order to collect data. Data is transmitted via satellite connection to the ground-based data sink, and the tactical companies analyze the data and plan the attack strategies or defense strategies for the military groups. Wireless sensor networks can also be found in environmental monitoring. Here the application field focuses on different values measurable in the environment, such as gas concentration, light influences, or pressure. Usually those networks are deployed in unfriendly areas, which has to face extreme wet weather, cold or dry weather. An example is the Sensorscope project of Switzerland. Here, sensor nodes are deployed on a glacier, which measure the environmental data during the whole year. This means that they are also collecting the data when snow is falling or when it's icy outside, which requires a big buffer space for the data, because they only can transmit the data to the labs when they can communicate. This means when no snow and no ice is available. Event tracking can be found especially in traffic applications. In general, the sensor data must be analyzed in context focus. Event tracking offers also features for grouping, so which crowd is moving in this special direction? Do they build new groups and then go in different directions? Examples are found in vehicle tracking, like in the Wikinet and Sense IT project. For details, please look on the corresponding websites mentioned at the end of this course material. The last example is the automatization. Here we already got an example with the elderly living, so having automatization systems in your home. But automatization can be also applied in industry, looking at office spaces or production. The idea is to observe the process, so how is a room used, product accuracy, airflow, temperature, pressure, or access of a room. The main idea is that automation is co-located with the control of a system. For example, in industry, you want to control a system in order to reduce energy wastage by proper humidity, ventilation, or air conditioning control. An example for office spaces with intelligent buildings and automation is the Autone project, where you should look on the homepage when you want to have more details. Now we are finished with the applications and are nearly at the end. Let's conclude. Wireless sensor networks are available nearly everywhere. They have in common to collect data and transmit it to data sinks for further analysis. Wireless sensor networks must fit different requirements depending on the application scenario. So, being in your house, being outside at the glacier or near a volcano. Wireless sensor networks include devices with different equipment. They consist of constrained hardware concerning energy, memory, and computational capacity. Wireless sensor networks require resource-efficient protocols and algorithms in order to ensure a system's long lifetime, reducing manual input. Therefore, you have basic idea now what to look on to make a successful deployment. Finally, we have to give an acknowledgement. Special thanks goes to Holger Karl and his team providing basic literature to the topic wireless sensor network, where the material is online available under the following link: www.wiley.com/go/WSN.